Hi, thank you for your introduction. My name is Alex. I'm working at Nuro in the group of autonomy interaction research. Due to different reasons, today I'm going to present the talk in English, but anyway, feel free to ask any questions even in Russian, doesn't matter. Yep. The talk today is going to be devoted to the certified robustness, its fundamentals and current challenges. So let's go deep into it. Today, probably the major four directions would be, the first is what is itself certified robustness, its definitions. The second is about the different variants of randomized smoothing. Then we are going to look into what's going on inside high-dimensional cases. And the last one is about the certification of semantic perturbations. The first slide, like advertisement slide, who am I? I have a PhD in theoretical computer science in 2016. I'm a lecturer in Lomonosov Moscow University and MIPT for machine learning, computer vision. Currently, I'm more focused in deep learning theory. I'm making lectures since 2019. I'm a former Huawei scientific expert, also the leading scientist researcher from ARI, Artificial Intelligence Research Institution. And currently, I'm leading the autonomy interaction research at Nuro. Okay. What is robustness? Because certified robustness, yes, the major part of it, robustness itself. What is robustness in formula? Robustness in formula is the ability of machine learning algorithm A to provide similar outputs with the similar data. It means that having the same class of other invariant features, we would like to have the same output. It could be same class, it could be very similar, I don't know, scalar data or something. Probably we can divide this robustness into two types, generalization and adversarial. Generalization, this is a data set issue. When algorithm needs to be robust, if the data set to evaluate, it differs. Sometimes significantly, and we can treat this difference as a distributional shift from the training data set. And when I'm talking about adversarial robustness, this is noise issue. When algorithm needs to provide a similar output with respect to both clean and noisy images. For sure, then this noise, model of noise is the topic to study itself. But now we'll consider the adversarial robustness, the last one. Adversarial robustness topics, they also can be different directions inside adversarial robustness. The first one is perturbations, or they're also called adversarial attacks. This is how to generate noise to fool the neural net. Second one is defense, how to diminish the influence of adversarial perturbations. And the last one is a certification, or sometimes it's called verification, how to provide theoretical guarantees on the noise level, which is not fooling the neural net. And we are going today to concentrate on the last one, certification or verification. Okay, let's go into definitions. Throughout the talk, we'll consider the neural net function f of x, which is a classifier to k capital classes. We have d-dimensional input and k classes. Usually, we have neural net as h of x, which is a mapping from d-dimensional to k-dimensional, and f of x is this argmax of this h of x. And we have two approaches here, deterministic and probabilistic. Deterministic approach, where we need to find the class of input perturbations S, and S is dependent of X and F, so the classifier output doesn't change. So more formally, we would like to find out the S in such a way where f of x plus delta is equal to f of x, where delta is inside this class of perturbations S. And probabilistic approach, where we need to find the cluster of perturbation, which is dependent in addition to some p. P here means some probability, subject to the probability of having the same output is equal to p. For sure, like the probabilistic approach coincides with deterministic approach when we have p equals to 1. At the same time, we have inverse task. Suppose we already know the perturbation class S, or this knowledge is provided for us by some task dependency, and we would like to understand, to measure the probability P of having the same classifier output under some class of perturbation S. So we have here again the probability of retaining the same class. And we need to infer somehow this P. From the first point of view, it could look like a very simple task, but it's not, because usually the perturbation class consists of enormous number, sometimes even infinite, of perturbations. That's why we need to somehow estimate this P with some level of confidence. Okay, I'm going to skip this technical slide. We could use very simple equations, and we can obtain that having the local Lipschitzness guarantees us the certification. But we have a couple of problems. The first problem is the certified radius can be much bigger than the local Lipschitz vicinity S. And the second, probably maybe is the major one here. This is very hard to provide the adequate, not tending to zero Lipschitz constant for any industrial, like very deep neural network. So we need to do something additional here. Okay, and let us go into maybe more applied approach. And first of all, let us provide very, very rough and brief taxonomy. I would say the adversarial robustness. Here we have two ways of defenses: certified and empirical, because currently we're talking about defenses. And for empirical defense, the major one is adversarial training. It's quite old and very well known approach, but today we're going to concentrate on the theoretical approaches. And inside the certified approaches, we have again the division into probabilistic and deterministic. Deterministic is probably the first one to be researched. We have multiple theorems here. Unfortunately, this approach is a little bit far from being applied on the industrial, again, neural networks and the big data sets. So much more used for now. This is randomized smoothing approach, and let's go into it. First of all, very short slide concerning the difference between empirical robustness and certified robustness. When we're talking about empirical robustness, this is the upper bound on the true robust accuracy. But this is only valid until the new and probably the stronger attacks appears. But when we're talking about certified robustness, this is the lower bound on the true robust accuracy. So we can prove here that no one attack can be worse, can provide us worse performance than the current certified robust bound. But as I said, this is theoretically proven, and no one attack can beat it. This is nice. Okay. When we're talking about adversarial examples, one simple analogy, maybe even not analogy, observation, I would say. And this is observation about the classification boundaries. And it seems like a very curved boundary leads to adversarial examples looking very similar to new ones near the classification boundary. So we, here on the right, we could see the classification boundary, and two classes is a blue one and orange one. And when we have an example near this spike, and spike also from the orange class, But if it is near blue class, it seems like it's hard to understand whether it belongs to blue one or orange one class. So this very spiky nature of boundaries can lead to really dangerous adversarial examples. So the idea is to smooth it, and smooth it. How to do it? To provide additional classifier. And this additional classifier, the process of providing it is called randomized smoothing. And to be honest, this is test time augmentation. We would like here to mitigate the boundary effect, and we would like to work with additional classifier g of x, where what does it mean? So we are smoothing the input with epsilon and with additional epsilon. So we are researching here the additional perturbations, and epsilon is from Gaussian distribution. So, and we would like to understand the argmax of probability where even the smoothed output is equal, the class of smoothed output is equal to C. And the main result here is if the initial classifier is robust under Gaussian noise, as you can see here, then any new classifier, then the new classifier G is robust under any noise. This is nice. This is the main theorem from Cohen in 2019. And this is sort of theoretical results here. So where we have this robust radius, R capital, this is equal to sigma over 2, and here phi inverse phi of PA minus inverse phi PB, where PA is the probability of the first class, of the main class, and PB, this is the probability of the second class in terms of probability. And the tightness of radius, so for any perturbation which is bigger than R capital, there exists a base classifier with satisfying all these conditions and probabilities, so as the smooth classifier will not provide the correct class. How to train this robust classifier? Initially, it was proposed very simple approach, just to train the base model with Gaussian noise, just to be robust to Gaussian noise, yes. And so any other training specific tricks aside simple augmentation are not provided. Okay, so we even have the how to do this inference, but let's skip it. What is interesting here, so we can plot the certified accuracy versus the radius, the input radius of attack, and we can see here the very nice looking, I would say, waterfalls, and the waterfalls just because the trained model is robust usually under some R which is less or equal than R capital. That's why we have a gradually diminishing certified accuracy, and some point it just drops to zero, drops to zero, drops to zero. Okay. These slides are going towards certified fundamentals. And let's finish with certified robustness with its fundamentals in terms of randomized smoothing. And what is randomized smoothing? This is smoothing distributions as Gaussian and the normal LP of perturbation, which is the epsilon ball. Usually, at least in the original work, is L2, but we can use different LP. For example, L1, L0, L infinity, and something like this. The drawback of randomized smoothing is that it requires multiple inferences. And when I say multiple, it means really big number. So it's not one, for example, 5 or 10. Usually it's 100 or 1,000, or probably even more. And certified robustness is better than empirical adversarial training in certification, but worse with clean performance. Too much time to train for sure. Okay, but what if we do not have the ability to train the robust classifier? So we already provided with some set of pre-trained classifiers. How to increase the certified robustness here? And there is an approach. It's called the idea of black box smoothing. So we need some denoiser, D capital here. And if we can use this denoiser after we already add some Gaussian noise, then we feed the denoised images to the off-the-shelf classifier, which is already provided by us for somehow, and then use the majority rule load. And here, yes, we can see this notion of smooth classifier, and the only difference with the previous notations here, the capital D. And D is here denoiser. So initially we add in noise, then we denoise it, and then we just using these simple notions. For example, for F, we would like to have the same output class C. And here you can see that we have this. We can use some classifiers in the cloud from Amazon, Google, Microsoft, Clarify, etc. Doesn't matter. Denoiser, we can train it with two losses for, if you're talking about computer vision, for example, it could be trained with two losses for every Gaussian sigma, for example, MSE loss and stability loss, where just classification cross entropy. So this is the noise image. This is the denoised image when we use when we train classifier with MSE, and this is when we added the stability. For example, it's not so smooth, so nice looking, but in terms of classification, this image is much better. But here we also needed to train the denoiser, as you can see. We need to train it, we need to play with different coefficients for different losses. But what if you would like also to use the denoiser also from off the shelf? And currently, you know, probably last 2 years, we have multiple papers devoted to diffusion models. For example, one of the original ones is denoising diffusion probabilistic models from 2020. And we can use it for certified robustness as well. Here we combine these two pieces, the off-the-shelf state-of-the-art classifier, which is trained in clean images, and we have the denoising diffusion model. And this is also pre-trained. So what we need to do, we need to add noise, we need to denoise with the denoising diffusion model, and we need to apply the state-of-the-art classifier. And the results are really good, I would say here. So we have a 14% of improvement over the prior certified state-of-the-art, and an improvement of 30% over denoised smoothing that have been published previously. Okay, but previously we talked only about the scalar output for when we have like k classes. Let's consider the vector-based function f, for example, feature vector from from the d-dimensional space to d-capital dimensional space. So the smoothed versions G, here we will be using this very same notion as before, but previously we added here the equality sign, like f of x plus epsilon is equal to class C, but here we don't have it. We are just smoothing the vector output. In this case, the following relation to Lipschitz function can be established. So it turns out that if we can add this additional property of having the length of this feature vector in L2 space to 1, then g of x is L Lipschitz and L2 norm, and this Lipschitzness having a very, very nice looking coefficient is the square root of 2 over p sigma squared. Yeah, that's nice. What to do next? We can establish a beautiful geometrical fact useful for the few-shot classification. So if we given an input x from d-dimensional space and the embedding g from d to d capital space, the closest point on the decision boundary in the embedding space is located at a distance gamma, and this gamma yes, has some formula. It's not very complex. This is depicted here to the right, and this delta is the smallest perturbation that is needed to go to jump out of the correct class. Yeah, so we can, and if we have some specific carefully designed perturbation, to be honest, it should be orthogonal to this boundary. We can jump out of the correct class C1 into the incorrect class C2. And it turns out that we can combine a couple of results for Lipschitzness and for this adversarial impending risk. So L capital and gamma. And we can infer very simply the certified radius for few-shot classification for vector functions. And this is very simple notation. This is gamma over L. And this work has been published the previous year on EURIPS. This is our work with colleagues from Scotech. And it provides us one of the first, I would say, approaches for certified robustness for few-shot learning. Okay. As I said previously, the randomized smoothing, this is the combination of smoothing distribution like Gaussian and normal perturbation. And using LP balls is neither necessary nor sufficient for perceptual robustness. For example, certification is only for much smaller regions than human can do, to be honest. Just a very short remark about physical nature of LP balls. L2 corresponds to the power of signals, L1 corresponds to the pixel mass, infinity corresponds to the noise and camera sensors, and L0 corresponds to the practical patch robustness. And let's talk about high-dimensional case in computer vision. So this perturbation delta is usually measured by LP norm, and it turns out that P equals to 1 and P equals to 2 are the only special cases where we could have this nice looking formula initially obtained for L2 norm, but later it was extended to L1 case. And unfortunately, these are the only examples of non-decreasing with the input dimension D of this radius. For any other P, we have R, which is inversely proportional to D. So bigger dimension D, the smaller radius R. And for example, taking into account that in computer vision we have dimensionalities of thousands, or probably even millions, it means that this radius, this certified radius, is super negligible, and we don't know what to do it in practice. So, and from the work of Kumar, we can see that this RP radius is sigma over 2d to the power 1 over 2 minus 1 over p. And when we have, for example, p which is bigger than 2, this R is tending towards 0. And the most important case for computer vision, as we've seen on the previous slide, this is P equals to infinity. This is how our perceptual system, human perceptual system, perceives information around us. And we can see this is the certified radius here is R infinity. This is proportional to 1 over square root of D. And so suppose we have the image of, for example, 1000 by 1000 pixels. This is the dimensionality of 1 million, but the square root of it is 1000. So anyway, it means that R infinity is going to be, and this, for example, quality inside the braces, for example, should not be, will not be very big. So we need to divide it by 1000, and R is going to be super small. So it's non-practical. And here we have the proof of it. We can see, for example, the differences between CFAR 10 when we have the D is thousands, and imagine it when we have D which is much more close to 1 million. So we can see the drop of radius. And for the most interesting case for us is the green one, the L infinity, and the radius is close to 1 to the 1/1000. So very, very small. But when we're talking about the, for example, p equals to 2, it doesn't matter whether it's CFAR or ImageNet, is not very stable. Okay, so what we can see, what we can infer from this fact, that any semantic, not any semantic, we can infer that for computer vision we need to consider something different. Why? Just because any semantic meaningful perturbation in computer vision leads to high L infinity perturbation. Why? Because even, for example, small translation in terms of like we can translate the image to 1 pixel or a couple of pixels to the right, to the left, or something like that. And it seems like for almost for every pixel we have quite significant perturbation. And when we're talking about L infinity, yes, we have significant perturbation. Any rotation leads to the same behavior. Any semantic meaningful perturbation like brightness, contrast, etc., etc. So, and taking into account that the dimensionality of image is usually very high, as I said, millions of pixels, so we do not have any practical certified radius because we have this R infinity. This is proportional to 1 over square of input dimension D. And what we could see practically that for semantic specific transformation like contrast and brightness, the error is higher than on clean images, up to 50 or even 60% on the special data set, which is called common corruptions. On ImageNet, common corruptions, this is it's about, I don't know, from 10 to 20 different special design corruptions like brightness, contrast, some specific types of noises that are usually to go and to be observed in the real world. But we can see, for example, for brightness and contrast, the numbers are error. And for AlexNet, for example, for error is 43. But when we using these different brightness and contrast images, we can see up to 100. For sure, with the better neural networks, with the better designed augmentation during training, we can diminish this bad behavior on brightness and contrast images. But anyway, it's still much, much bigger than in comparison to the clean images. Yeah, and the slide connected with my current engagement, my work, autonomous driving. And this is the same for safety critical applications like autonomous driving. For example, we can play with different contrast parameters, brightness parameters. And for example, here we can see the number of errors is really high, especially when we're talking about brightness. And why it is important? Because the autonomous self-driving vehicle needs to be operated for every weather, and for example, it needs to be operated for both for the day and for the night as well. And you know, like the brightness for the night will be very, very different. For sure, we can mitigate it by a number of methods, but still the problem exists. Yeah. So what is the proposal? The proposal is to certify not the whole image itself, but to do something more clever, certify semantic perturbations. And one of the first approaches here was the work from Fisher. It's called certified defense to image transformations via randomized smoothing. And usually this transformation are a family of transformation dependent on 1 or 2 parameters. So the dimensionality of semantic perturbations 1 or 2 dimensional is not 1,000, 1 million of pixels, for example. And here we are considering the rotations and translations. And smooth classifier is when we first it's designed in such a way, then we first apply the transformation beta. So beta are parameters, and transformation itself is gamma beta. And then we apply the function f. For sure, we need to take into account here the interpolation procedure, because after rotation, for example, we need to interpolate. We don't need to interpolate if we are using translation with integer parameters, for example, when we translate to the integer number of pixels, but when we are talking about rotation, we need to take into account the interpolation as well. Anyway, here we can still see the same formula, like sigma over 2 of this inverse phi of PA minus inverse phi PB. And finally, we have some working approach for computer vision for semantic perturbations. And this is a result. For example, it was applied to the stop sign, original sign, and when we have this adversarial different rotations, and we need to certify it, for example, for the parameter gamma from minus 30 degrees to plus 30 degrees of different rotations. And it has been done. So it's a working approach. Previously, we talked about different LP perturbation. For example, L infinity, and we have some bad consequences on computer vision that can be to some extent mitigated with semantic perturbations. But the smoothing distribution itself is under the research. So original and most of the follow-up works they are using Gaussian smoothing, but nothing prevents us from using different types of smoothing. For example, we can take into account uniform distribution or even Laplacian. But what about other types of smoothing distributions? And this is one of our works that also has been published previous year with my course and Nikita. We published it on IJCA the previous year, and it is concentrated not on the additive perturbations, because probably almost all research was concentrated on additive perturbations. But let's investigate the multiplicative parameters. Why it is meaningful and reasonable? Just because some semantical perturbations can be multiplicative. For example, gamma correction, where we need to have this this gamma correction parameter gamma and input image x, so the gamma correction is x to the power of gamma in computer vision. And it is multiplicatively composable, this gamma correction, and we can see the examples. For example, the original image is in the center, the gamma correction with 0.5 parameters to the left. It can be understood as a sort of process of adding brightness, and gamma correction with gamma equals to 2 is a little bit more, is looking like it was taken in the night, and it is to the right. Okay, and it turns out that when we are concentrating on multiplicative parameters, we can use different types of smoothing, and here we use a relay distribution. It's quite close to Gaussian, but still relay, because we need for positive support here and mean at 1. Why we need the mean at 1? Just because we don't need to have any perturbation, for example, and mean at 1 means that x to the power of 1 equals to x. And we could prove similar theorems, but they're a little bit more complex. Anyway, and the results are better for gamma, which is less than 1 in comparison to uniform, Gaussian, Laplace smoothing. So yeah, we could even play with different smoothing distributions. What about the compositions of perturbation? Previous work, again, were only about single perturbation, for example, only translation, only rotation, only gamma correction, or something like that. But in reality, in the real world, we have composition of, I don't know, of very, very different transformations. The forward theoretical estimation of certification is really difficult. So let's try inverse probabilistic task, as we talked in the beginning. Here, the proposal is to use Chernoff-Kramer inequality, or this is sort of Markov inequality corollary, to provide the statistically grounded estimations for this P, as we talked before, for the certification. And here, perturbed radius is already given. For example, we have here the parameters of brightness from -40 to 40%. We are playing with it. For contrast, different parameters. For rotation, different parameters, like for example, degrees of rotation from -10 to 10 degrees. And here we are combining these transformations. And what is important? So for this inverse task, we can play with any semantic perturbation and any composition. And here is how to the scheme of this approach. Let's not go into very detail, but yeah. So we can even play with this inverse task with different with different transformations, their compositions, and this work was published the previous year on a triple AI conference with my colleagues from Caltech. Yeah, I would say this is one of the first approaches covering this inverse task for certified robustness. Okay, I have a couple of slides, so let's go in. Our talk is going to the end. But yeah, what I have shown for now, these are sort of, how to say, the original works touching the, for example, the different problems of certification. For example, the composition of transformations, or for example, different smoothing distributions, or different LP boundaries, LP radius when we are looking into the epsilon ball of perturbations. But later some works introduced to take into account more and more different types of perturbations, more and more types of interpolation errors. And here I would like to refer to this work called TSS, or transformation specific smoothing. So the authors would like, the authors did in this work some sort of taxonomy, and they researched a number of different formulas concerning different types of transformations. So sort of unifying works has appeared currently in the literature, and this is good. It turns out that the topic itself researched some initial has been researched for some initial ways of what can be done for some specific cases. For example, as I said, smoothing distribution, LP balls, inverse versus non-inverse tasks, and now sort of sanctification of knowledge type work has been impaired. What also I would like to say is that some later works introduced approaches to apply certified robustness to other types of computer vision tasks, because previously everything what has been said today were only about the classification, but for sure we have multiple different tasks in computer vision, for example, detection and segmentation. And currently we also have some approaches that are dealing with these tasks. For example, for detection, it's mostly about certified robustness for regression, because we can see, for example, here the bold rectangle are the usual detection bounding box, and the dashed one are, for example, outer and inner, like upper and lower bounds for regression here. Also for certification for segmentation, here for example, usual ground truth segmentation is, we can see it to the right, is here. But when we can like attack it with some perturbation, we can have really, really bad segmentation. But if we can allow for us to abstain for some portion of image to certificate, we can still have some sort of reasonable segmentation. But the white areas are areas when we abstain from certification. Yeah, and as I said, more and more works are appearing for now that are trying to certify that are trying to systemize the certification approaches, and very, very good, interesting work has been appeared this year from Professor Boley, and so it's called as a SOC, or systematization of knowledge. They have provided benchmark and leaderboard. And this is how the taxonomy of different certified robustness approaches can look like. So I would refer for someone interested in it to this work and to this really great paper. And the takeaway from this today's talk, that first of all, the straightforward certification L infinity is not working for high dimension input. And this high dimension input, this is the major concern when we are talking about computer vision. And it turns out that in computer vision, they don't need any LP, to be honest, aside from L0 for patch attack. But usually L0 also combines with other perturbations. So we need only L0 here. And semantic perturbations, it turns out, first of all, they can provide us non-diminishing radius because the dimensionality is 1 or 2 or 3 or something like that. But at the same time, they are much, much harder to certify because we also need to take into account the interpolation if you're talking about, for example, talking about computer vision. And if you're talking again about computer vision, the current challenge today, I would say this is 3D and probably non-rigid transformations of real world, because, for example, human body is non-rigid body. It is combination of almost rigid portions, but anyway, as a whole, it's non-rigid transformation. So we need to take it into account in order to provide better transformation-specific certifications. Currently, they are only for 2D images when we have very simple transformations like rotations, translations, I don't know, brightness, contrast, etc., etc. But in real world, we don't have only this, how to say, 2D image specific, 2D digital image specific transformations. We have, if you would like to certify something in the real world, we need to take into account that we could have this, how to say, photo camera or video camera taking the exposition from different places when we have different types of obstacles as well. Yeah, this is what is really needed for now. So probably that's all. Thank you for your attention. I'm open to any questions, and if you have any.
Yeah, thank you, Aleksandr. Super interesting talk, and I'm in no way an expert in this area, and this is still super interesting. Anybody, do you have any questions to Aleksandr? We have Q&A, we have chat. You can raise a hand and ask a question, and while you are gathering, let me probably comment a little bit on that. Back in '84, there was a groundbreaking work of conjuring the structure of images. In that work, he have introduced a family of images with basically different resolutions, and have proved that convolution with Gaussian kernel is the only transformation that keeps the. А можно я по-русски? Да. И доказал, что свертка с гауссовским ядром является единственным преобразованием, которое позволяет строить семью изображений с разными разрешениями, сохраняя топологические особенности. Из этой работы выросли там, в следующем же году работы Дебишье про вейвлеты и там Мале, ну и вся эта французская тусовка. Соответственно, физики то же самое называют теми самыми. Господи, все слова из меня выпадают, что по-английски, что по-русски. По-русски одни слова из меня выпадают, по-английски другие слова выпадают.
Эти множества не пересекаются.
Да, калибровочная инвариантность. Да, когда мы на разных разрешениях видим разную ситуацию. Вот. Комментарий, собственно, состоит в том, что, возможно, значительная часть адверсарных атак, она убирается через калибровочную инвариантность изображений. Да? То есть, рассматривая нормированные изображения в разных разрешениях, мы, возможно, получим некие оценки относительно того, что происходит. Да? Ну, то есть, очевидно, что patch-attack, оно, например, понижением размерности убирается. Да? То есть у нас была patch-attack большая в L1, мы сделали smoothing, and it disappears. И как только мы переходим к стопке изображений разного разрешения, вероятно, мы, вот работая с такой стопкой, не с одним изображением одного разрешения, а со стопкой изображений разного разрешения, мы можем, вероятно, получить некие результаты относительно их устойчивости к разного рода атакам, в том числе и в бесконечность. Ну, потому что, опять же, там тот же сдвиг, после сглаживания он оказывается малоразличим. Да? То есть то, что у нас бесконечность было в одном разрешении очень большим, после сглаживания оказывается довольно небольшим. Да? Мы сдвинулись на 1 пиксель, и у нас в исходном разрешении все очень сильно изменилось. Да? Мы перешли на разрешение в 4 раза меньше, у нас изменение очень маленькое. Вот. На словах, конечно, это легко, в формулах это не такая халява, как на словах рассказать, но, вероятно, в этом месте что-то такое лежит, и, возможно, там есть какой-то способ сертифицировать некий набор алгоритмов относительно некоторого набора атак.
Okay, let me just rephrase the question, initial question. The proposal is the following: take into account, for example, pyramid of images. If we're talking about images, so we can use different dimensionality. For example, we can interpolate them, for example, increase or decrease, also to add some additional inputs, noise. It could be Gaussian kernel, for example. If we are going to look into different resolutions and with different input transformations, like I don't know, noising, based on Gaussian kernel, probably it could be, first of all, could be easier to remove adversarial attacks, and then second is to provide better certification. this is the nature of creation. But yeah, my answer is the following. Yeah, for the first one, this is definitely the case when we can remove some or most of the adversarial examples. And these were one of the first approaches how to provide some sort of empirical defenses. For empirical defenses, we need to do some sort of noise, denoise, or something like that in the input, and like 99% of attack will be removed, and you will be fine. Unfortunately, there are some, and it was like 5 years ago, something like that. Unfortunately, there are some sort of specific, if you know in advance what types of resolution, different resolutions you are going to use, which type of interpolation are you going to use, and which type of noise you are going to use. If you know in advance these parameters of process of providing you the new inputs, you can still mine a very fine-grained attack that can still beat it. So this approach is good for most of the empirical attacks, and this is sort of empirical defense. But when we are talking about the worst case, for example, about this certified defense, it's not working, unfortunately. So that's why, for example, when we have the certification by smoothing, we need to take into account not just a single, how to say, one example of adding noises. So we need to take into account the whole, the infinite number of images with different noises. For example, we need to add like many different noises. That's why we need to have here from 1,000 to, I don't know, 100 of thousands of different images with added noises, and only having the good enough statistics, probably like continuous number of images, we can infer some certification. This is the case.
Okay, thank you. Anybody having any more questions to Aleksandr?
Okay, probably this is because I was talking in English.
Oh, well, it's like not that much problem in English, but for me and for many of my colleagues, that's a pretty distant topic. Mm-hmm. And that's the first time I have heard of certified robustness. Probably not too many people in our among our attendees can figure out something about that. All right. Thank you so much, Aleksandr, for your report, and it's really interesting. And
thank you for the invitation. I would encourage everyone just to look into this direction, because it's sort of combination. First of all, the groundbreaking results in the current, I don't know, classifiers, neural nets, etc. But at the same time, you are going to research the theoretical grounds of it, not only just to play with the very cool new techniques. You need to think about how to provide some grounds, some theoretical grounds on every nice, because sometimes you can provide like 100% of accuracy, something like that, but adding a very small number of noise, the accuracy will be diminished to almost zero. Why? And this is the theoretical grounds of providing you the understanding why and what to do with it. So I would really encourage people, to work here as well. Okay.
Thank you.